When a massive star depletes its thermonuclear fuel, it undergoes a violent explosion known as a supernova. This is often considered the death of the star, the end of its luminous life cycle. But depending on how things go, the star's iron core may be crushed into an ultra-dense soup of elementary particles known as a neutron star, or even wilder, a black hole, a region of time and space where where gravity is so strong that light can't even escape. When these stellar leftovers find themselves orbiting a living star like our sun, something interesting happens. If the two objects are close enough to one another, then material may be lifted off of the surface of the companion star and fall into orbit around the neutron star or black hole. Soon it forms what we call an accretion disk as it spirals inwards due to an interplay of gravity and internal friction. As it does so, it heats up, reaching temperatures in the tens of millions of Kelvin, thousands of times hotter than the surface of our sun. This hot material emits a huge amount of high energy photons, which we see as X-rays. We therefore call these systems X-ray binaries, and we need specialized space-based telescopes to view and to study their physical properties. At Caltech, I've primarily focused on using one of these observatories, the Nuclear Spectroscopic Telescope Array, or NuSTAR for short. NuSTAR takes images of the X-ray sky while also measuring the energy and the arrival time of each individual photon that it sees, making it an ideal instrument for studying the array of phenomena that we see from X-ray binaries. For example, when a neutron star accretes, it may trigger runaway nuclear burning on its surface, resulting in an impressive but short-lived flash of light as its entire surface is enveloped in flames. I analyzed NuSTAR observations which caught not one, but two of these explosions. And I looked at how material was lifted off of the surface of the star, and I analyzed spectral and timing properties in order to find the composition of the material, as well as the distance from the Earth to the neutron star. More recently, I used NuSTAR to perform rapid follow-up of a newly discovered X-ray binary. When it first appeared on the sky, we didn't know if it was a neutron star or a black hole, but we did know there was an accretion disk. By looking at how the emission from the disk was actually distorted by gravity, I was able to determine that it was in fact a black hole. By actually probing how the central object dragged space and time around it, I found that it was spinning way too fast to be a neutron star. If it were a neutron star, it would tear itself apart. So, studying the physics of these objects and how they accrete can tell us a lot about bigger questions in our universe, such as supermassive black holes in the centers of galaxies. Because X-ray binaries evolve on timescales that are reasonable for a graduate student to study, we can use them as analogs for these larger black holes which evolve on much longer timescales. I like to think of X-ray binaries as, each X-ray binary as a sort of corner of the larger puzzle that our universe presents us, each telling a unique story about the hottest, densest, most energetic regions of space. Thank you.